All right, so probably the most important thing, all right, the is that the Earth's magnetic field protects life. All right, so we really don't think that life would have been possible um, on the Earth, at least not the life that the life that we know, um, without the Earth's magnetic field. Because what happens, of course, is there are what are called cosmic rays, right? Mostly from the sun, but there are actually cosmic rays that come from deep space as well. And so what happens with these cosmic rays is with the Earth's magnetic field, they get deflected, as I mentioned before, by the Earth's magnetic field, and they will, for the most part, be if they do end up crashing into the Earth, that they will crash into the Earth in the North and in the South Poles. All right, right? We'll explore that in just a little bit. But so that these things will that most of their energy would be lost in the upper atmosphere, not in other words, not harming creatures on the Earth. Although there is some harm, right? Obviously, there is some of these cosmic rays that get through all the way to the surface of the planet Earth. All right, I already mentioned the Van Allen belts. These are radiation zones that the astronauts need to be cautious of when they pass through there. Um, all right, but most space travel is below the Van Allen belts. These radiation zones are out pretty far from the Earth. It's yeah. Anyhow, all right. So now what about these charged particles when they actually get really close to the Earth and in fact hit the atmosphere? All right. So that's actually what we call the aurora. The aurora borealis is the one that happens in the north, and the aurora australis is the aurora in the south. All right, so these are when charged particles interact with the atmosphere, basically heating up the atmosphere and causing large amounts of electrical current, and that electrical current will interact with um, basically it heats it up. It excites the nitrogen molecules and any oxygen molecules that it encounters, and what happens is it's really an interaction between the electrons in these molecules. All right, so in fact, it's just the outer electrons in the molecules. The outer electrons go up into a slightly higher state, and that's a very unstable state for them. And then when they drop back down, they emit light, and so they're called the northern lights, or the aurora borealis, as it's known in the north, or the aurora australis in the south. And they're pretty amazing. You don't usually see them, um, south. Like for example, in let's say upper state New York, very rarely you can kind of see you can see some of them. You generally have to be in much higher latitudes, like up in Canada or up in Alaska. Like when I saw them, it was when I was in Alaska. Um, many years ago. I was actually in the Navy, and we went to Juneau, Alaska, and so you know I got to see the aurora borealis. Um, I mean, it doesn't happen every single night, uh, and sometimes they're pretty spectacular colors. Sometimes they're just they're kind of you can if you just type in the auroras on YouTube, you can see them. People film them all the time. I mean, they are pretty interesting, but they're charged particles interacting with the Earth's magnetic field. That's what they are. All right, now what we're going to do is turn to the Earth's atmosphere. And one of the basic things is, where does it come from, right? How did we get the atmosphere? And we're extremely lucky. We wouldn't be here if there weren't an atmosphere of the Earth, right? I mean, the atmosphere, allows us to live, right? So it's this veil of gas around the Earth, and the gas is actually has changed since the formation of the Earth. We believe that originally there was no gas around the Earth, and by the way, the atmosphere is trapped by the gravity of the Earth, right? So that's something that people don't really think about too much. Is that the Earth's atmosphere is only around the Earth because we have a relatively strong gravitational field. It's really the gravity that holds on to the atmosphere. For example, our moon, right? It's actually a fairly large moon, but most gases, or the common gases that we encounter in the Earth's atmosphere, will not stay on the moon, right? Because the atmosphere, the gas molecules, if the moon were to have an atmosphere, maybe just temporarily, let's say, those gas molecules would reach escape velocity very quickly. They would heat up because of their exposure to the sunlight, and would easily reach the escape velocity. Remember, escape velocity is the minimal velocity to leave a world and never come back. All right, so even if the moon gets some gases around it, even temporarily, they will not stay. Whereas the Earth holds on to the atmosphere pretty well. Whereas Mars, for example, doesn't hold on to its atmosphere very well at all. And that has more to do with the fact that Mars doesn't have a magnetic field, right? Its atmosphere has been. Well, we'll talk about that more next when we discuss Mars. All right. All right. So the atmosphere of the Earth. Where does it come from? Right. So let's look at a couple of some facts that we know about the atmosphere. So there is the troposphere. That's really where most of the weather comes from, or all the weather. Sorry, all the weather is in the troposphere. Above that is called the stratosphere. There's actually different layers of the Earth's atmosphere, but for what we're discussing, there's just the troposphere. And so the troposphere would be where, if you were to rise in a balloon, for example, and measure the temperature. So what happens in the troposphere is the temperature goes down as you go higher and higher and higher. And then you reach a point where the temperature begins to go up again. It gets it gets hotter and hotter and hotter. And so actually each time the temperature changes directions, that's actually a different part of the atmosphere. But anyhow, we're just calling anything above the troposphere the stratosphere. All right. So like I said, there are different regions. Anyhow, within the stratosphere is a region called the ozone layer, and that's another region of protection. So this is notice it's above the troposphere, and all, for the most part, the mountains are all below this. In fact, most of the atmosphere is below the troposphere. Most of what we consider the atmosphere. The atmosphere just gets thinner and thinner and thinner until you're finally up in space, where there's virtually no atmosphere at all. All right, so anyhow, what is this thing called the ozone layer, and how is it protecting us? All right, so here let's see. So let's move on. So basically, the ozone layer is the it's the O3 molecule. Okay, so the thing that we breathe, that you and I breathe, and animals all across the planet breathe, is the O2 molecule. It's two oxygens bonded together. When the oxygens get higher and higher in the atmosphere, the ultraviolet light will interact. So ultraviolet light from the sun will interact with the O2 molecules, and they will be cause, well, I mean, it's complicated how it actually happens, but basically the O2 molecules interacting with the ultraviolet light will cause O3. So it's three oxygens that are bound together, and that's what we call ozone. That is exactly what ozone is. And now, so what ozone does is it absorbs ultraviolet radiation, which is very harmful to life on the Earth. Like if ultraviolet radiation was to just penetrate down to the surface of the Earth, it would be extremely harmful. In fact, that's part of the reason when you go to the beach and stuff like that, you put on sunblock, is to block the ultraviolet radiation. All right, because some of it does get through, but not very much because of this ozone layer. All right, so this is what the Earth's atmosphere is made mostly of nitrogen molecules, about 78%, and then 21% is oxygen. And that was not always the case. The oxygen actually comes from plants, right? 21% of the O2, 21% of the air, you captured some air in a balloon or something like that. 78% of it would be nitrogen. These are two nitrogen molecules bound together, and then two oxygen molecules bound together. That would be 21%. And then the rest of it would be the other gases in the atmosphere. All right. And so there's a lot of other gases. One of the most important ones is carbon dioxide, CO2. There's some ozone as well. Usually not close to the surface. One way that you can tell that there's some ozone around, by the way, is if there's a lightning strike. If there's a lightning strike nearby, you can actually smell the ozone. It's got a very distinct odor. There's water vapor in the atmosphere, of course. That's why it rains sometimes. There's also the noble gas argon as well. At any rate, that's besides the nitrogen and oxygen, these ones right here, carbon dioxide, ozone, water, and argon make up about 1%, and there's some other stuff there too, but it's so minor. Just as a comparison, carbon dioxide, the CO2, is primarily the atmosphere of Mars and Venus. Mars has an atmosphere much less dense than the Earth, about 100 times less dense, and Venus, surprisingly, has an atmosphere about 100 times, roughly 100 times more dense. The outer planets have so the giants, right? Jupiter, Saturn, Uranus, and Neptune have mostly hydrogen atmospheres. They're large enough to trap the hydrogen atoms within their atmosphere. All right, so this is the greenhouse effect. I'll talk more about this in the next video.